So, good morning, students. In the Unit 2 load flow studies or load flow analysis, we are going to see how to derive power flow equations and that will lead to formulation of load flow problem. So, let us see how to derive power flow equations in this class. So, kindly watch the video. Thank you.
Flow equations. So in this video tutorial, we'll be talking about the very common power flow equations that are often found in textbooks and classrooms, but we're going to be looking at them from an intuitive perspective. This is part 1. So when we have a conductor that spans from bus 1 to bus 2, this conductor or the transmission line has some impedance and to model this impedance we have to have resistive component and a reactive component, and that essentially equals Z is equal to R plus JX. The R is the resistive component of the transmission line, and the X is the reactive component or the reactance, and then Z is called impedance. So the impedance is the resistive plus reactance, okay? So another way to describe impedance is a term called admittance. And admittance is essentially 1 over the impedance, right? So that's the admittance. If we think about it, impedance is the amount of impedance that the current will receive if it goes or if it travels from bus 1 to bus 2, right? Impedance, which kind of makes sense in the English language. And then admittance is the reciprocal of impedance, or 1 over the impedance. So admittance is how easy the current is allowed to travel from bus 1 to bus 2 through this transmission line. So admittance is 1 over the impedance, and that also equals G plus JB, where G is called the conductance and B is called the susceptance. Okay, so next let's talk about the voltages. So let's zoom in here. Okay, so the voltage on bus 1, we'll call it VI, right? Don't mind the subscript for now, it's very important for later. So VI at some angle tilde I. And so the voltage on bus 2, we'll call that voltage VJ, okay? And then the angle of that voltage is tilde J. So we have 2 different voltages, the voltage on bus 1 and the voltage on bus 2. Okay, so let me make these a little bit smaller. Okay, so now let's just talk about these subscripts. Now these subscripts are important because the power system is obviously not a 2-bus system. Okay, the power system is very big, very large, and so we need these subscripts to define each individual buses. Now if we want to determine the current that's flowing from bus 1 to bus 2, how would we do it? Now the simplest way to think about it is current is equal to the voltage drop between bus 1 and bus 2. So we'll say that we have the voltage of bus 1, which is VI at some angle I, minus the voltage on bus 2, which is VJ, right, at angle J, and then we divide that by the impedance, which makes perfect sense, right? Makes total sense. Now let's move that over here. Now the other way to describe this current is if we knew this impedance, right? If you knew Z, and if we already knew the voltage, so the voltage between bus 1 and bus 2. So V, let's call this V12. So if we already knew what the voltage is, which means we already know what these 2 terms are, and we know what the impedance of the transmission line is, then the current is equal to the voltage between bus 1 and bus 2, which is this voltage here, which is again this voltage there, there, you divide that by the impedance of the line, which is what we said over here, right? Makes sense. Okay, so now let's try to use this admittance. We said the admittance was y is equal to 1 over z, okay? So if y is equal to 1 over z, then what if we just took y, right, the admittance of this transmission line, and then we just multiply that by V12. That still makes sense, because all we're doing is, instead of calling this impedance, we're going to call it admittance. And look, our equation is so much more simpler, right? It's just admittance times the voltage drop between bus 1 and bus 2. Now let's make this smaller. Now if we were to do this particular equation with respect to a multi-bus system, how would we do it? Meaning, let's add some scripts to this equation so that we can define the current to all of the buses in our system. So we would do that by this method, and this method is very much documented in a lot of textbooks. So we're going to say I, which is basically akin to this current here, or akin to the current that's flowing through the transmission line. But we're going to say the current in the ith bus, right? That is equal to the sum of the currents, and we're going to call this J, to the n number of buses in the system. And so the summation of Yij, right? Yij times that by Vj. So now this is the way to define current in all of the buses in our system. And that is equal to essentially the current generated at a bus, okay? The current generated at a bus minus the load current on that bus, okay? And we'll cover this later. But it's essentially, this is the equation that we're very much interested in. Okay, so now that we talked about current, our next step is to talk about actual power, which is defined by S, right? The apparent power. But before we talk about this, if you haven't subscribed already, please go ahead and do so by clicking on the bottom right corner of the screen. Click on the subscribe button and subscribe to this channel. Now, if you have any questions, click on the link that's shown on the bottom of this video, and it'll take you to a forum, right? The forum is hosted by generalpack.com, and it serves the purpose of asking questions and the community responding to those questions. Go to the forum at generalpack.com and ask.
So in this video we saw about the formulation of power flow equation. In the next class we will be discussing about Gauss-Seidel method. So Gauss-Seidel method is the next video, which is important question, either procedure flow chart or flow chart, or a problem from it may come in university exam question paper. So the next video is important. Kindly watch it. Thank you.